I want to interpret what a passenger will feel inside an elevator. And then what happens if you're in free fall here? So the question that really kind of begs the answer to right now goes something like this here. So what happens if you're on a weight scale? Okay, so now what I want to do here is that I'm going to imagine Carlos on a weight scale. So you could imagine that here I am. I'm on this weight scale, right? And so when I'm thinking about this weight scale, then here's Carlos. And so when I'm thinking about this thing here, you could imagine that this is the ground, and that right there is the weight scale. So now that I'm on a weight scale, let's say that how do I say this here? So if I'm on the ground and I'm stationary, note that stationary or constant velocity in Newton's laws are identical. Oh, what am I doing here? So if they're identical, what am I actually seeing here? What I'm seeing here is that I can't tell the difference between the force of gravity and the weight scale pushing up here. So this would be the weight scale. And in this scenario here, what you're seeing here is that the force of the scale reading is then going to be the same as the force of gravity. So these guys are going to look exactly like this here. Now, what I'm going to do here is that I'm going to make some assumptions here. And the assumptions that I'm going to say here is that Carlos has a mass or a weight of 960 newtons. So whether I'm moving at constant velocity or whether I'm stationary, I'm always going to have this value here. Now, we got to be really careful here. So is it the ground that's pushing up on Carlos? Or is it the weight scale that's pushing up on Carlos? It is the weight scale. But the ground is pushing up on the weight scale, and the weight scale is pushing up on the ground. So let's go look at this thing here. So now, what am I going to do? I'm going to put Carlos in an elevator. Okay? And what we found here before was this, that if I look at, so now I'm in an accelerating elevator. So the first case that we want to look at is that we want to look at upward, acceleration. So if I look at an upward acceleration, what do I know? Well, I know that the weight scale has to push harder on Carlos. Just like we talked about over here, in order to accelerate something that was moving at constant velocity, we have to increase the tension in the cable. But here, it's not the cable that's working on Carlos. It's actually what? It's the force of the scale. So the force of the scale has to act, more on Carlos to increase his velocity here. And if I choose the same acceleration as we did before, what do we find here? Well, we find this. So for starters here, we said that the weight scale was this much when Carlos was at rest. Now we're accelerating upwards. So if we're accelerating upwards, we already know what the N2L equations are. What we're saying here is that in this case here, that being positive, this being negative, we then say that the net force acting on Carlos in this case is then going to be the F of the scale minus mg, and now this is ma. So when we do this, you're going to see that the scale reading is now going to have the same thing that we saw last time, that same equation. And if you plug in the numbers, what you're going to find here is that the scale reading increases to 1,070 newtons. So you could see here that there's an increase in scale reading of 70 plus 40, 110 newtons. That's an increase. And that means here is that we have to increase the force acting on Carlos by 110 newtons in order to keep him accelerating at at 1.22 meters per second squared for the acceleration. And then I can do the exact same thing here. Now we have a downward acceleration. And again, this is the exact acceleration as before. And what we saw here is that according to our picture as before, that this guy stays the same, but it's the force of the scale that must decrease. And then in this scenario, we're picking it this way because we're speeding up in this direction. So if I do the same type of analysis as we did before, we're going to see that this time gravity is positive, but the force of the scale is now in the negative direction, which then tells us, as we did before, that the scale reading now changes. And the way it changes is that it now reads 833 newtons. This is a decrease, right, in scale reading from we were at 960. So now that should be what, 60, 70. It shouldn't be 110. It should be, what is that number? So if I look at the reading here, it should be 960 minus 33. So 960 minus 33 should be 100 and, what is that, 27? Yes, I believe that's 127. 127 newtons. So there's a decrease in the scale reading. That means you have to apply less force in order to keep accelerating. I mean, you have to apply a smaller force in order to keep Carlos accelerating downwards at that value here. But there's something really interesting about this thing here. And it's really this question here. What would the scale read if the elevator went into free fall? The scale reading be if Carlos is in free fall. Well, if we really look at this thing, so if we're in free fall, then what this really means here is that in the limit as A goes to G, when I'm looking at the scale reading, and now, of course, I'm going down, this is really the limit as A goes to G of M, G minus A, and you could clearly see that the reading here goes to 0. So what does this mean? How can a scale reading be 0? Does this mean that Carlos has no weight? Right? That's what we term the term weightless. Am I weightless because the scale reading suddenly reads 0? In other words, maybe the more appropriate question, did Carlos lose all his mass? And the answer is no. It's not that he lost all his mass, it's just that the scale reading is 0. And what this means here is it means the following thing, that any time an object is in a state of free fall, all weight scales will read 0. So if an object is in a state of free fall, then all weight scales read 0. And this is a state of weightlessness. This is a state of weightlessness. And so then that means if you say the word free fall, that is the exact same statement as weightlessness. If you're in a state of free fall, you're in a state of weightlessness. So the question is, how do you get into this state of weightlessness? And the master, Newton, was the guy who figured it out. And that there's actually, it's known as Newton's mountain. He literally has this in his Principia, which was published in the 16th century. It's pretty impressive here. And what it is here is it essentially says this: for long range trajectories, one must take the curvature of the Earth into account. You have to take it into account. And what we find here is that when you look at the Earth, what you find here is that the Earth actually has a curvature, of course. Right? So there's a curvature. So the question is, how much is this curvature? So it turns out that if you travel 5 kilometers, you travel out, then what you're finding here is that the distance from here to here turns out to be roughly 5 meters. And it turns out that if you drop an object from 5 meters and you ask how long does it take to fall, it's 1 second of fall time. So what ends up happening is that Newton actually conceived of this, and typically it's known as Newton's mountain. And you imagine that you have a mountain, and then you have the earth. So when you're looking at this scenario here, what you're seeing here, right? Here's our pale blue dot here. What he does here is that he imagined that there's a cannon on top of this mountain. And what you do here is that you shoot this cannon. So in other words, you take a shot, the ball goes and it hits the ground. And then you continue to shoot faster and faster. Well, I don't have to just keep drawing this. There's an app that's available that I'm gonna show you here. So what I'm gonna do here is that I have this set up already, and let me show you what I have here. Here's an applet of Newton's mountain. And what you're seeing here is the following thing here. So there's the cannon, and then there's the speed. So if I fire this thing, right, you can see the path here. So as I start to increase this path, or this shot, and if I keep increasing it, so this one's not scaled right, by the way. So if I then take this shot again, you can see it goes faster. But if I go fast enough, you could see that it's starting to account for the curvature of the earth. But now, I think the way this applet is set up here, I think it's around 7,000 or so. Look what happens. Instead of falling into the earth, it falls around the earth. So if you go into this scenario here, what I'm going to do here is that I'm going to just take an image of this thing and bring it into the notes here, is that if I was to then come in back into my OneNote here, is that if I was to shoot this fast enough, okay, if I was to shoot it at just the right time, instead of falling into the earth, it's moving fast enough so that the curvature is falling away at the same rate. What's that speed? Well, the speed in order to orbit has to be 5,000 meters every 1 second. In other words, 5 kilometers per second, which is about 18,000 miles per hour, which is incredible here. And so what's cool about this thing is that it does this thing here, is that, you know, anytime you have a satellite, right? Anytime you have a satellite, so if this is Earth right here, right? And you have a satellite that's orbiting Earth. This satellite is actually moving at 18,000 miles an hour. It's in a state of free fall. And the definition of a state of free fall is that you only have one force of gravity. There's only the force of gravity acting on you. In fact, there's a special case where I forget his name. I think it's Bruce McCandless or something like that. He was the first guy that became untethered from the shuttle. And they clocked him as he went all the way around the earth. And you know what his speed was? His speed was 18,000 miles per hour. And so anytime an object is in a state of free fall, it has to be this way. And you may have heard of the vomit comet, which is exactly the same type of thing, where you get into the state of weightlessness because the airplane is in a state of free fall. In other words, if you have an airplane like the vomit comet, what you're seeing here is that they shoot up, right? So as they're moving up, they then get into a state where they turn everything off, and then all of a sudden you get this hump here. And during this phase, the airplane is in a state of free fall. So the airplane is in a state of free fall. But if you're in a state of free fall, what does that mean you're doing? You're in free fall. You're falling, and everything else around you is in that state of motion, so you get the sense of floating, which is kind of wild when you think about that. But that's what we mean by this state of being free fall. But if we continue to think about free fall has some really bizarre issues here. So if I look at free fall and the force, let's talk about this. So when we drop things in free fall, there's something special about this, right? So suppose one drops an air filled and a lead filled tennis ball. So what actually happens here? So you could imagine that I'm doing this type of thing, right? I have a tennis ball right there. It's filled with air. Now I have a second tennis ball. And so when I'm looking at these guys, what I'm seeing here is that as I drop these guys, one of these guys has lead shot. And the crazy thing about this is that if I drop them, these guys here will hit the ground at the same time, right? This being the air and this being the lead shot tennis ball here, they hit the ground at the same time, right? So
is free fall motion being in a vacuum? Is that the same thing? Or?
It is the same thing.
Oh, okay.
Yeah, it is absolutely the same thing. And so we know already that they both, hit the ground at the same time. But you know what the common answer is to this? We ask the question, why is this? And you know what most of the answers are? They say they have the same force of gravity. Common answer. They have the same force of gravity. That's the common answer. And my response to this, no way, not possible. Which one weighs more? The air-filled tennis ball or the lead shot tennis ball? Clearly, this has a bigger mass, therefore a bigger force of gravity. They do not have the same force of gravity acting on them. They have different forces of gravity acting on them. And so as a consequence, We need Newton's second law to answer the question of why do they have the same acceleration? And that's because if you look at the force of this guy here, right? This force of gravity is small. This force of gravity is big, but Newton's second law says that it's inversely proportional to the mass. So you simultaneously have a bigger mass, and a bigger force of gravity. And so it turns out that these give you the same value of G. So if we look at this mathematically, you could imagine that I have a block versus two blocks. So if you're looking at these blocks here, what you're seeing here is that one of these blocks is mass m, this one's m and m. So therefore, when I look at the force of gravity, this guy's mg, this guy's 2mg. But wait a minute, this has one mass, this has twice the mass. So you could see here that the masses cancel out, giving you g. The reason why they accelerate at the same rate is because their force to mass ratio is the same. So this mass independence shows up in one, falling objects, objects sliding down inclines, and also pendulums. Different mass objects have that. They're independent of mass, which is, phenomenal. And a lot of times people don't really get to see this, in firsthand. And there's a really fantastic video that you probably have already seen, but man, is it worth seeing. Let me go share that with you here. So check this out. So what I'm going to do here is that I'll play just a little bit of this thing, but this is Brian Cox, where they have the vacuum chamber, where they're dropping, this a bowling ball and feather here. So I'll play part of it, but not all of it. So check this out. They're going to drop these two. Right? No surprise, right? No surprise. But then they do it all over again. And what they're going to do here is that now they've taken all of the air out. And now they're going to release them again.
2, 1, release.
I have seen that thing so many times. You got to admit, that is pretty badass. I mean, I can't tell you how many times I've seen that. It is really, really good. Yeah, this is, and every time I see that, you would think that it would get old. To me, it has not gotten old. That is awesome. That is freaking sexy, if you want to say it that way. It doesn't get better than that. Okay,